Chapter 18 is on electrochemistry, which is basically using oxidation reduction reactions to generate an electric current, and then that can be used to power things like your iPhone or your Android phone. And the first thing you'll notice when you start looking through the notes booklet is that this chapter has a lot of group work in it. And I'm going to work through the stuff, and you can follow along with me. And I did have a thing in there where you could turn in the notes booklet for a chance for a prize. Obviously, since we're not meeting in person, we're not able to do this. And so that, unfortunately, won't apply. And then the other thing you'll see as we go through this chapter is that I've modified the material somewhat to streamline it, make it more straightforward, simplify it, and shorten it. And so, as I mentioned a minute ago, it's about oxidation reduction reactions, redox reactions, which we first covered in Chem 1. And then we're going to connect all that to delta G and K. And you'll notice at the beginning of the chapter there are 4 topics listed. We're only going to be covering topics 1 through 3, and so there will be 3 videos on this, and we will not be covering topic 4 on the list. We're just going to do topics 1 through 3. And here is topic 1. It's a review of oxidation and reduction, and then it describes balancing redox reactions. We're going to see, you'll see in a little bit, we're going to really shorten this section. And so the way we would have started this chapter if we were meeting down in Beach 104 live and in person is that you and a partner would have been doing a little group demonstration. And I'm going to show it to you in some pictures, where you would have been dipping a nail made of iron, Fe, into a solution of copper 2. And so you can see here, here's the nail, and then there's the blue solution of copper 2. And so then what we would have done in class is you put the nail in there for maybe 10 or 20 seconds. And then when you pull it out, if you look carefully at your screen, you'll see that the nail now has a copper coating on it. And so the blue solution here contains Cu2+. And that's the blue solution, and then we dip the nail in there. And so this is a redox reaction because we're taking something that is not charged, and then it is becoming charged. And so that has lost electrons because it becomes plus charge. And then the copper 2 plus is missing 2 electrons. That makes it a positive ion. And then over here, it has claimed 2 electrons, and it's taken them from the iron. And this is a pretty straightforward reaction. If we just ask the question, how many electrons were transferred in that reaction? We can say that the iron lost 2 and the copper gained 2. So for this reaction, 2 electrons have been moved. It's the same 2 lost by the iron, gained by the copper 2 plus. So this one is 2. We'll see some more complicated reactions later. And here's kind of an up-close picture of what's going on in this. And so, and this will kind of give you an introduction to batteries. In this reaction, there's an iron atom here, and it's being oxidized to iron 2 plus. In order for that to happen, 2 electrons need to be lost. And I don't really like the way that this image is shown where these are clustered, but those are copper 2 plus ions over here. And so you can imagine here's a copper 2 plus ion, and it is picking up those 2 electrons, and then they are becoming copper atoms. And so this is a replacement type reaction. And so what's going on is now we have Fe2 plus. And so this is being done in one container. What we'll see later in the chapter is that if you can split this into two half reactions and then put some barrier in the center, you can generate an electric current. And this is basically what a battery does, is that it does the oxidation reaction in one half, it does the reduction in another half, and then in between it is where you put your device that you want to power, like your iPhone. And so that's the key to a battery. Is the two reactions are done in compartments, and then you generate a useful current. And so this chapter, when you think of the word electricity, just try to think of electrons flowing through a wire. That's what electricity is. And here's a review of some terms from back in Chem 1. We use that phrase oil rig. Oxidation is loss of electrons. Reduction is gain of electrons. The reduction phrase actually comes from, it's a reduction of the positive charge. So we saw in the copper example, it went from 2 plus to 0. So its charge is reduced because you're adding negatives. That's where the phrase comes from. So this is, everything in here is phrased in terms of electrons. Reduction is gain of electrons, oxidation is loss of electrons. So the oxidized reactant here is the Fe solid. You can only choose reactants for this. So this is the Fe. It's not the Fe2 plus because that's the product of the oxidation. The reduced reactant is the copper 2 plus because it's gaining the electrons. You have to be careful. You can't put the copper, you gotta put the copper 2 plus. These parallel terms describe the action that is going on. So the oxidizing agent is the item that is doing the oxidation. If you can name these two up here, you just do a crisscross effectively. The oxidizing agent is the item that has been reduced because it oxidized the other item. And so this just goes here, and then the reducing agent is the Fe. And so once again, for a problem like this, you never choose the products. The only answers can be the reactants. And if you can get these two, just crisscross them and you'll be okay. Here's a reaction that is slightly more complicated when we think about counting electrons. We're going to be doing a lot of that this chapter, counting electrons. And before we actually do this reaction for the counting, I'm going to review the oxidation number rules from Chem 1. They're in your textbook all the way back on page 161. That's about 600 pages earlier than where we're at now. And so I'll briefly review the rules, and then that will take us through the rules that we use this chapter. And so I'll refresh our memories on these. I'll put up here like oxidation number rule. Some of these you may remember, hopefully you do. Elements. These are materials like NaO2. If you have a pure element all by itself, with no charge written by it, oxidation number is 0. They're the easiest. Just as long as there's not a charge written on there, it's a 0. When you do have a monatomic ion, for example, Na plus, O2 minus. These are also quite straightforward because whatever charge is written by them is the oxidation number. And so these are for just monatomic ions though. When we get into polyatomics, we'll have to put a little tiny twist in there. So when you deal with compounds, remember a compound is a neutral mixture of different ions or elements. And so when you have a compound, it's neutral, so all the oxidation numbers will add up to 0. When you have a polyatomic ion, all the oxidation numbers add up to the charge on the polyatomic ion. Here's a simple example, which also we'll talk about Rule 4 at the same time. If you look at like NaCl, the total oxidation numbers there have to add up to 0 because it's a neutral ionic compound. When we have a metal in a compound, we just use what we know about the periodic table to get us that charge. Hopefully you know at this point in your chemistry career that sodium is in column 1 of the periodic table. So the charge on sodium is a +1. So when we think about metals and compounds, we just use our knowledge base of the periodic table. If you had something like calcium oxide, CaO, the calcium is in column 2, so it's a +2. When we have nonmetals in compounds and polyatomic ions, we're going to let the rules on oxygen and hydrogen dominate. And I'm going to give you sort of a simplified rule. There are exceptions, but for anything we deal with in chapter 18, oxygen will be a -2 when it's in a compound. If you have the neutral element, it's a 0, but when it's in a compound, it's a -2. There are exceptions, but for our purposes, it's a -2. Hydrogen, once again, there are possible exceptions, but for our purposes, when hydrogen is in a compound, it will be a +1. The halogens, like chlorine, bromine, iodine, for example, when they're in a compound, they will typically be -1 unless oxygen is present, and then oxygen will dominate the conversation. And so that OX there is short for oxygen. And so here's a simple example that will review a polyatomic ion. If we go back up here, change the color. Here's a quick example. If I look at the polyatomic ion, Cl(O2-). If Cl was in something like sodium chloride, the Cl would be a -1. But here we have to consider oxygen as the dominant force in this. There are 2 oxygens. They make a -4 total. The whole ion has to come up to be -1. So in this case, the Cl is a +3. And so depending on how things are paired up, let oxygen run the show. It'll be a -2 each. And then the Cl will be a +3 in this example. And so we have to be careful on the chlorine, but like I said, let hydrogen and oxygen dominate the rules. This is a simplification in a sense, this will work for our purposes. So let's go back to that reaction now, and we can check our rules. And so the number of electrons transferred. In a problem like this, we have two elements on this side. All the oxidation numbers on the left side are 0. There are 4 hydrogens, they're all 0. When we look at the right side, let's not worry about that 2 yet. So about a water molecule, oxygen is in a compound, so it's a -2 for that oxygen in the water molecule. Each of those hydrogens is a +1. I'll draw the water molecule. Notice the total charge comes out to be 0. We're basically pretending it's ionic, even though it's only partially positive on the hydrogen. We're sort of faking it and pretending it's totally charged. And so we give it a +1 oxidation number. And so those two hydrogens right there both went from 0 to 1. Now we can deal with that 2 in front of that water. There's another water molecule involved. If I draw it out, see those charges on there, and you can come up with this a few different ways. You can say there are 2 oxygen atoms, both of them become -2, so they have gone from 0 to -2 each. There are 2 of them. The number of electrons transferred is 4 in this case. You can also look at it from the standpoint of the hydrogen. There are 4 of them. Each one went to +1. So 4 times 1 is 4. So you can get that 2 different ways. The species that is oxidized is the H2. Because it has lost electrons. Now the only other answer that's possible over here is O2. That's what is reduced. And then the item that is reduced is the oxidizing agent, so that is also O2. And so there'll be some practice for you on your own in the notes booklet, and then I will be giving you some extra practice coming up. We're going to see the next part is going to be modified. And so let's do a simple balancing of a redox. And so here's a simple reaction. We have 1 aluminum plus a copper 2 plus goes to aluminum 3 plus and a copper. If we think about this in terms of mass and atoms, there's 1 aluminum here, 1 copper over there. So in a sense, this is balanced along those lines. But if we look at the charge, the left side is a +2, the right side is a +3. And so it's not balanced in terms of charge. The total charge on each side must be the same. And so we're going to have to do a little bit of modifying to balance this. And ultimately, we have to get the electrons to cancel. And so we would split this up into half reactions, which this is what happens in a battery. One side of your battery, the anode, actually has the oxidation half reaction. And so here's the oxidation half reaction. It's aluminum, goes to aluminum 3 plus, and it loses 3 electrons because it's oxidized. So I'll let you pause the video and you try to write the reduction half reaction and think about where the electrons go in a reduction if you try to write that half reaction. So you're just going to use copper in that one. Try to include the electrons. So here is the copper half reaction. Copper is being reduced I didn't put my phase symbols on there, but that's okay here. I'll put it on the next slide. So copper is gaining 2 electrons. They would go in the reactant side because they're going in the reactants. They go on that side, and then when we balance this up in a moment, you see we've got a 3 there and a 2 there. We have to make those the same. Be like common denominators. And so if we do want to finish that balancing, I guess I'll pop back to this slide. I'll keep it official. Put those in. So I have to find some common number of electrons that I'm going to cancel. Obviously, if one has 3, the other one has 2, a common denominator type thing, if you're adding fractions, the equivalent of, would be 6. And so I would multiply the top reaction by 2, double everything, 6 electrons. I multiply the bottom reaction by 3. Triple everything. And now when I add these together, the 6 electrons that are on the right side and the left side will cancel out, and I'll have a balanced equation. And so the balanced equation for this one will end up looking like 2 aluminums plus 3 coppers. So there's the balanced equation. Hopefully you can read that nicely on the screen. And now when we look at it, we would say, is it balanced in terms of mass? And we would say it's got 2 aluminums here, 2 here. That's good to go. 3 coppers, 3 coppers. And now the total charge on the left side is a +6. 3 copper, 2 pluses. Total charge on the right side is +6. And so this is all balanced up in terms of charge and mass. And so now it's balancing a simple reaction. If you look at this example down below them, it's got this very complicated ion called dichromate. And these are a little different because you notice there's an oxygen there. There's no oxygen over on this side. And so there's a series of steps to balance these. However, we will not be covering that this year. What I'm going to focus on, if you jump to chapter 6, or page 6, I'm sorry, not chapter 6. If you go to page 6, there are some problems that involve balanced equations, and it asks you to balance them. What I'm going to focus on instead, and this should be a great relief to you, is that I'm going to give you the balanced equations. I'm going to focus more on having you count the number of electrons transferred in balanced equations because that's the skill you need later in the chapter. And so if you jump to page 6, for example, I'm going to work through this example with you, and then I'm going to show you the other 2 equations that are very different than how that will appear very differently than how they do originally. And so here's a more complicated example. This is metabolizing glucose in your body. And the question is, it's a multiple choice question. It's how many electrons are transferred during the complete oxidation of glucose. You are welcome to pause the video and try this yourself and see if you get one of these answers here, one of them is correct. Otherwise, you can follow with me, but I would recommend trying it yourself first. Okay, let's get at this number. And there are multiple ways to do this. Personally, I would recommend looking at the oxygen because it starts out as an element. And so you know that all 12 of those oxygens have a 0 oxidation state. There are 12 atoms and 6 molecules of O2. So all 12 of those are 0. We know that. These oxygens are actually -2 each. the 6 in the glucose molecule. So they actually won't change, because if you look at the right side of this reaction, there are a total of 18 oxygens, because there has to be, because it's a balanced equation. All of those 18 oxygens are either in carbon dioxide or they're in water. And so all 18 of those have a -2 oxidation number. But only 12 of them changed. And so when you think about the total number of electrons moved, we only care about those 12 oxygens that went from 0 to -2. 12 times 2 is 24, and so that's the number of electrons that were transferred in this reaction. 24 electrons have been gained by the oxygen. It's the oxidizing agent in your metabolism. What ends up getting oxidized, if you did it that way, is if you tear apart that glucose molecule, so you have to trust yourselves. Those 6 oxygens are -2 each. They make a -12 total. There are 12 hydrogens, +1 each. That's +12. Glucose is a neutral molecule. So all 6 of those carbons on the left side have an oxidation number of 0, because the 12 and -12 cancel each other out. Let's switch over to the right side, and don't worry about the 6 for a moment. Like I said, if you counted the carbons, you could have done this, and you should have gotten the 24 also. When we look at carbon dioxide, each oxygen is -2, -4 total. That means each of those carbons is a +4 each. And so there are 6 carbons total. All 6 of them went from 0 to +4. And so 6 times 4 is also 24. So each carbon has lost 4 electrons. Each oxygen can only gain 2 per. That's why you need 12 oxygens. And so that is another way to get the 24, looking at the carbon. And carbon dioxide is a waste product for us. That means that the carbon has been completely oxidized. My camera cut off right when I was talking about carbon dioxide being completely oxidized. Like I said, when the video got cut off, it's a waste product. We breathe it out. Of course, plants grab some sunlight and turn it back into sugar for us. So carbon dioxide, like I said, is a waste product. So the other 2 reactions, if you look at page 6, there's a question on there that says balance the following in acidic aqueous solution. We skip that material. What I want you to focus on instead is I'm giving you the balanced equations. These are very complicated equations. You can see the ingredients, MnO4 minus and the Br minus, but you notice now there are some H pluses in there, and then on the product side there are some manganese 2 ions, some Br2s, and some waters. So what I want you to do, instead of trying to balance this, is copy that down and work on practicing counting the electrons transferred. That's a more important skill for us when we do batteries. And so that's the balanced equation. Pause your video, copy that down, and try to be able to count the electrons. You don't have to worry about balancing these. Number 3, also, don't worry about balancing it. I'm going to give you the balanced equation right here. It's in red here. There are 8 MnO4 minuses that react with 5 thiosulfates. You have 14 H pluses in there. 8 manganese 2 ions again. 10 sulfates, 7 waters. the key for you is to count the electrons transferred in the balanced equation. You'll see on the next slide, these will be extra credit problems for chapter 18. So that ends topic 1. And so here's what you should be able to do at the end of this. Go back to page 3 in the notes booklet, try those outside of class follow-ups. Here's the extra credit. This is due by Friday, April 10th. Count the electrons transferred in those page 6 balanced equations. You need to go back on the video a little bit and pause it and write down those equations. You have to send me a picture. It can be a selfie with you and your book or something, but you have to send me an image or your handwriting or something if you're using your Surface Pro that shows me your original work, and there'll be some extra credit available to figure out the number of electrons transferred in the 2 balanced equations that I gave you on page 6. Not the glucose problem, but problems 2 and 3. From your textbook then, this is sort of looking ahead. If you look at problems 29 and 30, these are at the end of the chapter. So these are on pages, I think, page like 771, I believe. I guess the book doesn't put that the number on there. These are at the end of the chapter. And if you can look at problems 29 and 30, if you can count the electrons transferred in those reactions, those problems will be a lot easier when we talk about batteries. Because when you do the battery problems, you have to know the number of electrons transferred in a balanced equation. And so that's really good practice. Problems 29 and 30, I believe it's page 771. And so that ends topic 1. There'll be 2 more videos. Topic 2 will be on how to make a battery, and then topic 3 will combine voltage and delta G together.